Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through problem set 18, the ideal gas law. First of all, let me just write this mathematically. This is the ideal gas law, and you'll probably have this memorized by the end of the class, and you'll be using this occasionally in future chemistry classes as well, so it behooves you to have it at least mentally on hand. And note that this equation here is a conglomerate of several gas laws, okay? We'll learn about Charles' law here in a second, but there are several like Graham's law as well that actually make up this equation. Okay, so this is actually a conglomerate. We didn't do an experiment and then find this equation. There are actually several different gas laws that people ended up looking at and then combine them into what we call the ideal gas law. And you'll learn later why we call it the ideal gas law is because we have to make various assumptions about it. And number one kind of talks about this a little bit. So which of the following are not characteristics of an ideal gas? Okay, so two of these here will be assumptions of the ideal gas law, and two of them will not be. Okay, I'll say that right off the bat. So letter A says the molecules of a gas have a little volume compared to with the volume they occupy. That is true. Okay, that is true. That is one of the main assumptions of the ideal gas law. And then when we learn later about what we call the van der Waals equation, where we take into account the volume of gases, because it actually does change, our pressures and temperatures a lot. This is one of the main factors, one of the main variables that we take into account, the volume of the molecules of the gases. So for the ideal gas law, that's one of the main 4 to 5 assumptions that we have with the ideal gas law. Letter B says its volume is independent of temperature. That is false, okay? Even if you look at this equation, you know that if you were to leave everything the same and change volume and look how it changed temperature, it's going to change temperature. Now, we actually call this Charles' law. And Charles' law, if we were to kind of just compare volumes and temperatures together, it would look like this. V1 over T1 is equal to V2 over T2, okay? Meaning when I increase volume 1, or when I increase volume in the second situation up, T2 has to go up, right? If V1, let's say V1 was 1 and T1 was 1, and if I put V2 at, 4, then T2 has to be 4 as well so that these sides can be equal, right? So mathematically, that's how it works out. But just in theory, when you increase the temperature, your volume is going to increase. Think about it like with the balloon. If you kept everything constant and all you did was increase the temperature which it was at, it would expand. Okay, that's just the nature of Charles' law. Okay, and that actually does happen. You'll find that even if you do stuff like that at home. Now maybe you won't be able to measure it precisely because we're making a lot of assumptions with the ideal gas law, but that general principle is true. So that means this is not a characteristic of an ideal gas law. Okay. That it's independent in temperature. It's actually dependent on temperature, okay? Dependent on temperature. All right, letter C says the density of all gases is the same. Now, I'm going to write an equation here that's a derivation of the ideal gas law here, but just bear with me. It looks like this, okay? And this is molar mass, okay? It's not actual mass. Now, the density of all ideal gases is the same. Now, assuming this is part of the ideal gas equation right here, if I left P, R, and T all the same, the density of all gases could not possibly be the same because every gas has different molar masses, unless they're really close, like maybe CO2 or sorry, CO2 and some other compound that has the same molar mass. Anyway, so as long as it has the same molar mass, it'll have the same density. But that does not mean that all ideal gases have the same density. In fact, most of them will not because most gases have different molar masses. So that is not an assumption in the ideal gas law. And then part D says gas atoms or molecules do not interact with one another. And that is true. That is one of the main assumptions of the ideal gas law. Okay, without that effect, we actually it would not be considered ideal gas law. And we'll actually take that into account in the van der Waals equation later on in the class, because this has to do with like intermolecular forces, whether that's attractive forces or repulsive forces, okay? So those do have an effect, especially once you get into higher levels of polarity, thinking of like, hydrogen bonds or dipole-dipole forces. Those largely affect how ideal gases would ideally behave if it were not for those. So those are the two that are the volume, the independence of temperature, and the density of all ideal gases are the same, are not characteristics of an ideal gas. And the other two assumptions are one, or I should say, here's 1, here's 2, and then this would be 3 and 4. 3 would be something to the effect of that gas particles have equal volume. I'll just put equal V here. And then the last one is that they have a random movement, okay, movement. They're not on a, set track or anything. They kind of hit into each other, and there's not any set pathway. All right, number 2 said, what would happen to the pressure of an ideal gas under each of the following conditions? Okay, so for each of these, I kind of want to show you a method that's really helped me to solve these really quickly, okay? Part A says, doubling the volume while keeping the temperature and moles constant. Okay, so what I want you to do is write down the ideal gas law and then put an X above everything that is changing. And in each of these questions, because they're asking how the pressure is changing, it's always going to have an X above it. If it were asking about volume or temperature, then that's what you would put the X above. But here in this case, it's only changing the volume in situation A while keeping everything else constant. So I'm going to designate the X's above only P and V. Now, why are we doing that? Because what I would ultimately like to do is put everything that's changing on one side of the equation and all the constants on the right side of the equation, okay? And then what you do is you say, okay, I know that PV is equal to nRT, but I don't know that one situation must be equal to a second situation, okay? And so what I can do is that because they're equal to the same constant here, I'm going to set them equal to each other. P1, V1 is equal to P2, V2. Now, you have no idea what the actual values of these were, but you do know by what they changed, by what factor they changed. And in this case, the volume 1 went from 1 to, 2, for example. Right? Now, what you can do with the first situation is really convenient. You can just call all this equal to 1. Okay, so I'm going to say 1 is equal to 2 P2. Okay, so now I just solve for P2 because P2 is the second situation of pressure that I'm solving for. You're always going to be solving for P2 in each of these situations. And so P2 is going to be equal to 1/2. Now, if you look at the equation, it makes sense, right? If P1, V1 is equal to P2, V2, if they have to be equal to each other, right? If this doubled, then this had to half if this is equal to 1, right? And so these have what we call an inverse relationship, okay? They as one increases, the other decreases. So when doubling the volume, my pressure gets cut in half. I'm just going to put 1/2 P2, okay? 1/2 P2. So hopefully this will start making sense once we move into parts B and C here. Okay, so part B says reducing the temperature by 1/3 while keeping the volume and the moles constant. Okay, so now I've got P obviously is changing, but they said the volumes volume is staying the same. It's constant, right? But the temperature is changing as well. So I'm going to move everything algebraically to the left and everything that's not changing to the right. So I'm going to put P over T is equal to now NR over V. Okay. Now I know that this set of constants must be equal to a second situation where the things where variables have changed. So I'm going to call this situation 1 and this situation 2. Now I know that they're equal to the same thing, so I'm going to set them equal to each other. P2, T2. Now you'll notice a pattern here. You'll be able to do this with anything. Now you'll probably recognize this as one of the laws of the ideal gas law that gets implemented into this equation. But there are going to be versions of this, such as maybe the following. You get PV over RT is equal to N. And then that is not necessarily one of the laws that you learn about, but this is definitely one of those situations where you could, where using this method could help you figure out, changes in gases, in gas laws. Okay, so in this case here, I've got P1 over T1 is equal to P2 over T2. I'm solving for P2, right? Every situation here, I'm solving for P2, and I'm going to substitute the number here that represents the T2, which they said it decreased by 1/3. So it's 1/3 of its original value. And remember, this whole situation here, I'm going to set equal to 1. So now I've got 1 is equal to P2 over 1/3, which if you remember, if we divide by 1/3, then it becomes the numerator. So we got 1 is equal to 3 P2. And then that means P2, once we divide the 3 over, is equal to 1/3. Now, does that make sense? If we look at the P1 over T1 equals a P2 over T2 relationship, as I increase one, the other one has to also increase, right? These are in a direct relationship. Or vice versa, if I decrease the other one also has to decrease. So in this case, this is now 1/3 P2. It's decreased by 1/3 of its value because the temperature was decreased by 1/3 of its value as well. Okay. All right, last one. It says quadrupling the number of moles while keeping the volume and the temperature constant. All right, so now we're only dealing with moles and pressure. So in my Pivnert equation, I'm going to put an X above the P and the N, right? And then move everything that's changing to the left and everything that's not to the right, and then set it equal to another condition. Okay, so now it's going to be P over N 1 is equal to P2 over N2, okay? So they quadrupled the number of moles. That means it's 4 times its size, and this is equal to 1, right? This is 1, so I'm going to put 1 is equal to P2 over 4. That means P2 is equal to 4. Now, that would assume that these have a direct relationship, and if we look, yeah, sure enough, they have a direct relationship. When I increase one, the other one also has to increase, okay? So I'm going to put 4P2, and that's how you'd go about solving these problems, okay? Now, I guarantee there's going to be a lot more complicated ones, like one I presented earlier, where maybe all variables are changing, right? Where nt is equal to r, and that means in this case, r is going to be your only constant, and r can never change; it's a constant. So you always have at least one constant, and you'll have the pv over nt. And let's say you're solving for p2 again. In this case, you could assume that all this is 1, and then you put in the various variables for each of these, depending on by what they change. So it's really helpful to understand the ideal gas law and how to manipulate it algebraically to solve questions like this. All right, number 3. On one cold winter night, you discover that your thermometer is broken, and you decide to use your knowledge of the gas laws to determine the outside temperature. In your warm 75 degrees Fahrenheit household, you'd fill a balloon with an ideal gas to a diameter of 1.56 feet. You place the balloon outside while it equilibrates with the cold. You measure the new diameter to be 1.51 feet. What is the temperature outside? All right, and then they want us to treat the balloons as spheres, which obviously is not perfectly true, but for this case, it actually makes it a lot simpler. So, in this case, if I look at the Pivnert equation and I put an x above anything that is changing, right? I'm looking at what? I'm looking at the volume change in the balloon, and there's going to be a temperature change, right? And we're pretty much assuming that everything else is constant. So what do? I move everything that's changing to the left, everything that's not to the right, and I get the following. V over T is equal to NR over P. And if it's true in one case, it must be true in a second case as well, and then that allows me to set them equal to each other. So I get V1 over T1 is equal to V2 over T2. Okay, and in this case, what are we solving for? Well, we're looking for what the temperature is outside, so we're going to call that temperature 2. We're going to say that's the second condition. So if I solve this algebraically first, I actually get the following. I get T2, V1. I'll just work out the algebra just in case so you don't get lost. But then I do that, and then I divide this over and multiply this up. So I get T2 is equal to V2 over V1 times, and then I'll just put T1 up here in front. It's actually in the numerator, but it actually it'll make it a little simpler for our math if we just put this in front here. Okay, so T2 is going to be equal to whatever my temperature 1 is, which they've given me, right, but in the wrong units, times the second volume, which we know is going to be in terms of what? In 4/3 pi r, and then I'm going to put r2 cubed over 4/3 pi r1 cubed, all right? So that's basically how we want to set this up algebraically first. Now, you can kind of tell already there's things that we can cancel and simplify this equation so we can do a lot less math. So here I'm going to cancel out the 4/3 and the pi, okay? And then I get r2 cubed over r1 cubed. In fact, if you get, because they gave us the measurement to us in a diameter, it would actually be easier if we put this in terms of diameter. Remember, diameter is twice the radius, right? Radius is just half of a diameter. So if I plug in d over 2 for r, I get the following for each one of these. So I get t over 2 is equal to t1, which we'll solve here in a second. Then I get d2 over 2, cubed, over d1 over 2 cubed. Okay, and then, or not over, d1 over 2 cubed. And then I can cancel out the halves here, okay, because I'm actually able to take out this cubed here. So it ends up being d2 over 2 over d1 over 2 cubed, and then I just cancel out the 2's here. And so ultimately, to save us a lot less math later, I can actually solve this as just d2 over d1 cubed. Okay. Now, the temperature that you need is always going to be Kelvin. I'll always assume Kelvin unless you can see a unit that involves Celsius. We'll never use Fahrenheit as is. It's not useful in any of the math equations that we use. So just assume that any temperature that you're given, just automatically change it to Kelvin. And it's really easy to change it from Kelvin to Celsius and vice versa. So in this case, if you did this right, the 75, the equation for this is 75 minus 32. So this is going to be the temperature that we have. Times 5 over 9, and then that's equal to ultimately, and then we'll add this to 273 for the Celsius. That way we get our 297 Kelvin, which is the temperature 1. That goes right here. So T2 is going to be equal to, I'm going to put 297 Kelvin Okay, and then in here I'm going to put D2. D2 is the volume or the diameter associated with the temperature outside, which is the lower number. This is 1.51 feet. Okay, and then I get 1.56 feet down here. My feet cancel, and then I just got to cube that. Okay, now if you do this correctly, you should get about 269.3 Kelvin, which is about negative 3.85 degrees Celsius, and they didn't tell you what unit that they wanted it in, but if they did, you could put any one of these numbers in, okay? So just remember that when we're using the ideal gas law, you always want to shift what's changing to the left, and then manipulate it so that everything that's only things that are changing are in your equation, in this equation right here. And then solve for the T2 or the P2 or whatever you're solving for, and then just plug in numbers as is. And just remember that the units that you want to use are specific, especially temperature. You always want that to be in Kelvin. One thing to note here is that the R constant, if you look at the R constant for the ideal gas law, it's 0.082057. Whoops. 057, and the units for this are really interesting. It's liter atmospheres per mole Kelvin. Okay, so this pretty much tells you the units of each number. So when we have PV equals nRT, right, if this R is accounting for every unit, the liter atmosphere, I got a liter in my volume, in atmosphere, and my pressure, and then obviously this is in moles, and then this is in Kelvin. Okay, can you see that? That's why we get this units, because it ends up canceling out all the other units. So just note, put these in the right units, and then rearranging this may have been confusing at first, but hopefully you're able to see that reducing it down first helps a lot more. All right, number 4. Number 4 says the first step in the industrial production of nitric acid is reacting ammonia with oxygen. Okay, then it gives you the balanced chemical equation, and then it says how many liters of NH3 or ammonia at 850 degrees Celsius and 5 atmospheres, are required to react with 32 grams of oxygen. Okay, so now what we need to do is do a mole-to-mole ratio between oxygen and NH3. First of all, we need to find out how many moles of oxygen this is so we can do that mole-to-mole ratio. So the first thing I do is do 32 grams of O2. Okay, and if you look on the periodic table, 1 mole of O2 is equal to about 32 grams. Okay, 32 grams. And then the mole-to-mole ratio between oxygen, so actually moles of oxygen and moles of NH3 is what? 5 to 4, right? 5 moles of oxygen are required to react with 4 moles of NH3. And then this will tell me how many moles of NH3 I need. Now, obviously, these 32s are going to cancel, and we're going to end up with something like 0.8. Okay, 0.8 moles of NH3. Now, if they were asking for how many liters of this was at STP, this would be a really easy question after this, right? Because all you would have to do is take this number, and if you remember that at STP, which is what? 1 atmosphere and 273 Kelvin, okay? At STP, 1 mole of any gas at STP is equal to 22.4 liters, okay? Hopefully, I don't know if we've reviewed that yet, but just know that this is true, okay? That the 1 mole of any gas at STP will have the same volume, okay? And all we would have to do is multiply this number by 22.4 to find out the volume. But because we're not at STP, we're at 5 atmospheres and 850 degrees Celsius, then we got to figure out what the actual volume will be. So in this case, I'm going to look at the Pivnert equation, and then look at the variable that I'm solving for. So now we're not just like looking at proportionalities and changes of one situation to the other. We're actually dealing with real numbers here, right? So I'm not gonna move everything to one side that's changing and everything else that's not. In this case, I'm just gonna isolate the variable that I need, which is in this case what? Volume, right? That's in liters. So I'm gonna put volume is gonna be equal to nRT over P. Okay, and then we're just gonna plug in each value. Now I got 0.8 moles. Whoops, 0.8 moles of gas here. And then my R constant is 0.082057. Okay, and then I'll just put in all the parts of the unit here. And my temperature has to be in Kelvin, right? And so I got to do 850 plus 273. That gets me about 1173, or 1123, sorry, 1123. So we got 1123 Kelvin all over 5 atmospheres, right? That's my pressure. Okay, and if you do that correctly, you should get about 14.7 liters. That would be how many liters? That'd be the volume of the ammonia that you would need to react with 32 grams of oxygen exactly. All right, number 5 says, suppose atmospheric temperature and pressure at the bottom of a ski run are -5 degrees Celsius and 713 millimeters of mercury. At the bottom of the run, the temperature and pressure are 0 degrees Celsius and 734 millimeters of mercury. How many more moles of oxygen does the skier take in with a lung full of air at the bottom of the run than at the top? Okay, so if I look at my PV is equal to nRT, okay, what's changing? Okay, I've got P is changing. Whoops. P is changing. Temperature is changing, and moles are changing. Everything else is the same, so I'm going to isolate them. I got a P over NT is equal to R over V. And that's also equal to a second set of conditions, which is equal to the same thing. So I'm going to label this situation 1 and this situation 2, and then set them equal to each other. Okay, hopefully you got the pattern down now. Now, if we look here, what are we looking for? We're actually looking for how many moles does N2 have, right? N2, assuming N2 is the bottom of the run, how many more moles is N2 than N1? Well, in this case, we're not going to be able to solve for numerical values for 2 different variables, okay? That's hard to do. And so what we're going to do is actually solve for a ratio, and the ratio is going to be N2 to N1, and that will give me at least a proportion by how much more N2 is bigger than N1, right? It's a ratio. So in this case, I'm going to isolate this algebraically to solve for N2 over N1. So if I do that, I get N2 is over here, N2, and then I switch that with P1, and then put T1 over here. So in this case, I get N2 is over N1 is equal to P2 T1 over P1 T2. So they're just flipped, okay? So now this makes it a little easier. If I look at the top of the run, though, I'm going to call the top 1 situation 1 and the bottom situation 2. T1 is going to be what, -5 degrees Celsius, but I never use Celsius, right? I have to put this into Kelvin, so that's going to be 268 Kelvin. And then my pressure up here is going to be what? 713 millimeters of mercury. Now, you could change this into atmospheres, but I'll show you why here in a second. You don't actually have to change this unit, okay? Temperature for sure. Temperature always needs to be in Kelvin, but pressure, I'll show you why it doesn't matter in this case that you change it to atmospheres. If it makes your heart happy, go for it. But I'll just show you here in a second the trick. So T2 down here is going to be they told us 0 degrees Celsius, which is what, 273 Kelvin. See, 273 Kelvin. Okay, and then P2, they said, was 734 millimeters of mercury. So when I plug these in, I'm going to put these 2 in first. So I'll put T2 and then P2 here is going to be 734 millimeters of mercury. Okay, let me just get rid of that 2 there for a second. And then my temperature 1, okay, this is temperature 1, not temperature 2. Temperature 1 with pressure 2 is 268. So then I get that, and then I get 713 millimeters of mercury for pressure 1 on the bottom here, and then I get a temperature 2 as 273, right, 273. So that's how we end up solving for this. That's how we set up this equation. And then we get a ratio of N2 to N1, not necessarily in terms of how many more moles, but by how much, by what percentage, or by what, in this case, proportion, there are more moles of oxygen on the bottom than there are on the top. So when you solve this, you should get about 1.01. Now, what does that mean? That means in a ratio of N2 to N1, N2 is 1.01 times bigger than N1, right? It would be as if we did this. But in percentage terms, which is what they're asking for, what that really means is that there is 101%, okay? That means it's 101%. Now, that doesn't mean 101% more, because this is 101% to a ratio of 100%, okay? Not to 1. And then that means, all that means is that there's 1% more moles of oxygen on the bottom than the top, okay? All right, so that's how you solve a question like this. You want to remember, do what we were doing before, where we take the variables that we're changing, put an X above them, solve for what we're looking for. Now, in this case, the hard part was figuring out what you were looking for, right? In this case, we were actually looking for a ratio between 2 variables, which is not super common, but it may come up on a test. And then solve for everything else. One thing I obviously forgot to go over is you don't actually have to change this to atmospheres, because these units will cancel. Even if you put these both into atmospheres, you'd end up with the same ratio, and it wouldn't change your answer. It would just make you do a few more steps to get to the same answer. So that's why we actually had to that's why we didn't have to use atmospheres. Kelvin, however, is on an absolute scale, and so we have to use that. Celsius, because Celsius can use negatives, it really jacks up our values, so we have to use Kelvin for that kind of stuff. All right. So this is how we solve for a question like this. And then solving for percentage, just make sure that it's ratios and percentages. Be careful with what you compare them to, but ultimately there should be 1% more moles of oxygen on the bottom of the run than the top of the run.